All right, I'll probably do example number 3 and 4 from 15.1 in this video. Now that we've covered a couple of different new antiderivative rules, we're going to make the problems look a little more complicated and kind of test us a little bit. So looking at example number 3a, we are finding the indefinite integral, the antiderivative of x squared plus 1 over the square root of x. Now a couple different things. First thing I notice, I don't know about you, but I notice this x to the 1/2, the square root of x, and I'm going to change it into an x to the 1/2. But then I also notice that I have a variable at the top and a variable in my denominator. And right now we don't have a quotient rule for antiderivatives. So we somehow have to rewrite this original problem into a rule that we do know. There is no such thing right now as quotient rule. So we have to somehow rewrite it into something different. Try something, see what you think. All right, here's one thing you can do. You could separate it into two different fractions and then reduce. What I noticed, just the first thing I thought of, was taking that x to the 1/2 and bringing it up. And so now he's an x to the negative 1/2, and it's being multiplied by that quantity x squared plus 1. But be careful, I still have now two different variables being multiplied together. And we don't have a product rule for antiderivatives. All we know right now is power rule. We don't have product rule or quotient rule. So I still have to somehow rewrite this into a problem that I do know. Okay, so what I'm going to do is I'm going to take this x to the negative 1/2 and I'm going to distribute it through. Remember that when we multiply, we really add the exponents. So now I have a new problem that says I want to integrate x to the 3/2 plus x to the negative 1/2 with respect to x. Now I have two separate terms, only separated by a plus or minus sign, and it looks like I can use the power rule now on each of these terms. So far I haven't done any sort of antiderivative stuff. All I've done is manipulate my original equation into a problem that I do know how to do. So now we still have to anti-differentiate using that power rule. Add 1 to your exponent and divide by your new exponent for each term. I ended up getting x to the 5/2, and remember dividing by 5/2 is the same thing as multiplying by 2/5, so that's why it turned into a 2/5. I'm going to add 1 over here, and so I ended up getting 1/2, but instead of dividing by 1/2, I'm going to multiply by 2 over 1, his reciprocal. That's how I got the 2, or 2 over 1. And then don't forget to add your constant of integration at the back. So your final answer should be 2x to the 5/2 over 5 plus 2x to the 1/2 plus c. If you're not sure you did it right, double check it by finding the derivative and see if it turns into what you started with. So that's kind of what I did to double check. I brought that 5/5 forward, just like I do when I take derivatives. I subtract 1 from the exponent, and then I did that for each term. And I ended up getting what I started with, so I know I got the correct answer. Okay, look at B. Looking at B, it looks like I have the quantity x squared minus 1 squared. And if this were a derivative problem, what derivative rule does this look like? Well, to me, this looks like a chain rule. But remember, we don't have product rule, we don't have quotient rule, and we don't have chain rule when it comes to antiderivatives. So we can't do this problem using chain rule. So what other technique can we use to rewrite this problem into a problem that we do know how? Hopefully you thought of foiling. Taking this x squared minus 1, writing it out twice, and foiling. Foil, distribute, combine like terms, and make it into a problem that we do know. So now we're integrating x to the 4th minus 2x squared plus 1 with respect to x. This problem and my original problem are the same exact problem. Now it just looks like a problem that we know a rule for. We can do power rule on each of these terms. Add 1 to your exponent and divide by your new exponent. That gives me x to the 5th over 5 minus 2x cubed over 3 plus 1x, remember your constant of integration at the back, plus c. Okay, so on those two problems, we had to manipulate it a little bit into a problem that we could use the power rule on. So we had to do a little bit of work before we could find the antiderivative. All right, so we know product rule. We know that if there's a number in the front, we can just leave it and find the antiderivative of the rest of it. And we know that we can find the antiderivative of each term as long as they're only separated by plus or minus signs. We're going to add 2 more rules now. We're not going to worry about these bottom ones, but we're going to look at e to the x. Well, if you remember, the derivative of e to the x is just e to the x. So what is the antiderivative of e to the x? Well, then shouldn't that just be e to the x also? But remember, it's e to the x plus c, because I could have any constant at the back and his derivative would be 0 and it would go away. So our new rule is that the antiderivative of e to the x is really just e to the x plus c. All right, we got another rule. E to the kx. So for example, if I have the integral of e to the, 5x. Because it is more than just an x, this is kind of like a power rule. But remember, we don't have power rule for integration yet. And so the rule, when I have a e to the kx, a number in front of the x, is the antiderivative of e to the 5x is e to the 5x divided by that 5. Oh wait, plus c. So the antiderivative of e to the kx is really e to the kx divided by that k plus c. I would like you to know those two rules. Okay, easy enough. Make sure that you practice. Let's do example number 4. All right, find each indefinite integral. So looking at this, I noticed that there was a 9. You could leave the 9 in the front, ignore them for a second if you need to, and then just find the antiderivative of e to the x. So we know now that the antiderivative of e to the x is just e to the x, but e to the x plus c. So I have the 9 that was there to begin with. I have the antiderivative of e to the x, which is just e to the x, and then I have my constant of integration. Not too bad, right? All right, so b looks a little bit different. On b, 9 isn't a coefficient in the front, so I can't just ignore the 9. This looks like my second rule of e to the kx. Remember that the antiderivative of e to the kx is e to the kx divided by k plus c. So on this example, the antiderivative of e to the 9x is e to the 9x divided by that 9 plus c. Okay? All right, look at c. This is the last one for this video. I noticed a couple different things on c. I noticed that there's a 3 in the front, so I could leave that out. And then I noticed that I have e to the 5/4 x, or u. It's just a different variable. So I should be able to take that 3, write it out in front, and then I have e to the 5/4 u, and I'm finding the derivative with respect to u. Change them to x's if that makes you feel more comfortable, but it's just a different variable, so don't be too concerned about that u. It's just a different letter. And so I noticed that this wasn't just an e to the u or e to the x, it's a little bit more. To me, this looks like an e to the kx problem. So I'm going to use my new rule where it says the antiderivative of e to the kx is e to the kx over that k. So over that 5/4. Well, what did I just do here? Well, instead of having in that triple layer fraction, remember from before, instead of dividing by 5/4, can I multiply by 4/5, his reciprocal? And then I had to bring that 3 that was out in front back. So I have a 3, I have a 4/5, I have an e to the 5/4 u, and then don't forget your constant of integration plus c. I'm going to make it look a little bit nicer by kind of bringing everybody together. So I have really a 12 e to the 5/4 u over 5 plus c. Okay? All right, practice some of your exponential antiderivatives, and then we'll do